Okay, good afternoon. Today I have planned to make a lecture about pore pressure in geomechanics in terms of my after course applied geomechanics for geologists. The lectures includes 6 topics. In final topics we will discuss pore pressure calculation in our geomechanical simulation program LithoStudio. Okay, let's go to topic number 1, applied pore pressure. It calls as applied pore pressure because in this topic we will discuss application and importance of pore pressure in geology and all geomechanics. When we hear pore pressure, the first that comes to us is drilling. Sure, the elevation pore pressure can introduce risks during drilling when we're using mud weight less than when pore pressure 1. Secondly, elevated pore pressure influenced on fault stability. As you can see here, the elevation of pore pressure can lead to fault reactivation. On the other hand, pore pressure depletion can cause significant deformation in a reservoir. The deformation includes subsidence, compaction, and permeability losses. It is especially observed in poorly consolidated and weak formation. Okay, let's go to a pore pressure definition topic. As you can see here, pore pressure is defined as a scalar hydraulic potential acting within the unconnected pore space. It's usually described in a relation to hydrostatic pressure that associated with a column of water in interconnected pore system from the daily surface to defined depths Z. Depending on salinity, hydrostatic pore pressure increased with depths in the rate of 10 megapascal for 1 kilometer, 1 gram for cubic centimeter, or 0.44 psi for foot. Pore pressure varies from hydrostatic to severe overpressure, which can be more than 2 times of hydrostatic pressure in a subsurface formation. Also, overpressures exist in many geological basins in the world. If the abnormal pore pressure is not accurately predicted before drilling or while drilling, risks and incidents will increase greatly. Likewise, pore pressure that is less than hydrostatic pressure is termed underpressure or subnormal pressure. So underpressure and overpressure together are composed of the classification of abnormal pressure. This figure shows the variation of pore pressure with depths from observation in one of the fields of Western Siberia. At relatively shallow depths, in this case about 3 kilometers, the pore pressure essentially hydrostatic before 3 kilometers, yeah? Essential hydrostatic. After 3 kilometers, between 3 kilometers and 4 kilometers, pore pressure increases with depths very rapidly, indicating that this formation are hydraulically isolated from shallower depths. The hydrostatic pressure and formation pore pressure in a typical oil and gas well are plotted and left figure. This is overburden stress, pore pressure, and hydrostatic pressure. This is difference called as overpressure. At relatively shallow depths, in this case less than 2 kilometers, Pore pressure is hydrostatic, indicating that a continuous interconnected column of pore fluid extends from surface to defined depth. And the depth is more 2 km. The overpressure starts, and overpressure increases with depth very rapidly, yeah? Implying that the deeper formation hydraulically isolated, as that been in previous case. By 4 km, the pore pressure reach a value close to the overburden stress, a condition referred to as the hard overpressure. Pore pressure gradient is more practically value. It's used in drilling engineering because it's more convenient to be used for determining mud weight density. This shown in this figure. Pore pressure gradient and given depth is a pore pressure divided by true vertical depth. The mud weight should be appropriately selected based on pore pressure gradient, wellbore stability, and fracture gradient before setting and cementing a casing. We will discuss a fracture gradient and wellbore stability in future lectures. The topic of our today lectures, this is only our pore pressure, under pressure and overpressure. The drilling fluid mud, it applied in form of mud pressure to support the wellbore walls for preventing wellbore collapse during drilling. To avoid fluid influx and wellbore instability in open hole, a heavier mud weight than pore pressure is needed. Okay, please see a figure on the left part of slide. In any permeable inclined formation, if a deeper overpressed section is connected to the shallower section by a permeable pathway, the pressures in such hydraulically connected formation can be calculated using difference of heights of fluid column. Is equation here. It can be called as hydraulic communication model. Now please note that the figure on the right part slide, it shows an example of calculating pore pressure in sandstone using this equation. When the pore pressure and fluid density in well number 1 are known, the pressures in other wells 2, 3 and 4 can be calculated using this equation too. Okay. If the formation is hydraulically connected and saturated with the same fluid as in this case, okay, and pore pressure in all 4 wells should follow as a single fluid gradient. In this case, this is oil gradient 0.9 gram per cubic centimeter. Okay. It should be noted that the permeability magnitudes and its variation may affect hydraulic connectivity of a formation. But so in extremely permeability formation, its shales, this application may be limited. Let's consider a situation where pore pressure, if they have different fluids. Pore pressure gradient is different for formation when we have any fluids. Yes, okay, it's oil, maybe gas, water, brine, etc. In each fluid column, the pore pressure can be calculated using previous equation with the density of fluid saturation in this column. If fluid pressure at the depths we know, fluid densities and depths of water-oil contact and oil-gas contact are also known. Then the pressures in other depths can be obtained by using previous equation. For instance, the gas pressures at depth A can be calculated using this equation, and pore pressure and at depth B can be calculated for this equation. Okay. This is example of pore pressure spatial variation. Please note that the figure A and this picture shows the depths 1,500 meters depth. And here near hydrostatic values of pore pressure are observed. Okay. The figure demonstrates that in addition to variations of pore pressure with depth, lateral variations of pore pressure are quite pronounced in some sedimentary basin. Note that in some areas, in general mostly close to coast, pore pressures remain hydrostatic at all depths. Okay. In other areas, our pore pressures is seen to increase for hydrostatic values at figure A to much higher values in greater depths. This is figure B and C. Thus, the detailed manner in which pore pressure change with depths varies from area to area, and any given depth there can be important lateral variation of pore pressure. The discovery of a centroid concept was made based on the observation that the shale pressure and sand pressure experience distinct local gradient. It should be known that the pore pressure in tilted sand doesn't match the pore pressure in shale due to the significantly low permeability in shale formation. In the case of sands, the pore pressure follows a hydrostatic oil or gas gradient depending on fluid it contains. Okay. And the sand formation serves as a channel for transferring pressures on deep, as explained in prior section. On other hand, this is not the case for shale formation. The shale pore pressure is typically attributed to disequilibrium compaction and generally mirrors the overburden or lithostatic stress gradient. In deeper layers, the shale pore pressure surpasses the sand pore pressure. Nevertheless, at shallower depths, the sand pore pressure outweigh the shale pore pressure. Hence, the centroid represents the specific depths where the sand and shale pore pressure become balanced. Pressure gradient and mud weight are expressed in metric units of specific gravity or gram for cubic centimeter. However, in oil and gas industry, pressure gradient and mud weight are often reported in area of English or United States system of units. The conversion of pore pressure gradient between United States unit and metric unit can be found in this table. In the drilling industry, pressure gradient in subsurface formation are usually converted to equivalent mud weight, EMV, as a surface for display and interpretation. In United States system or units, the units for pore pressure gradient is lbs for gallon or ppg, which is commonly used as the unit for pressure gradient and mud weight in drilling industry in the United States and some other countries. In Russian Federation and the countries of former Soviet Union, the unit of pore pressure gradient usually is metric system. Okay, let's go to the topic number 3. This is causes of over and under pressures. In the slide you can see a chart of causes of over pressures. There is very much causes of elevated pore pressure. They include thermal, tectonic, mechanical, dynamic, chemical causes, and every cause includes sub-causes. Okay, and let's consider basic causes of overpressure and underpressure in a future part of our lecture. Overpressures can be generated by many mechanisms, such as compaction disequilibrium, undercompaction, hydrocarbon generation, and gas cracking, aquathermal expansion, tectonic compression, mineral transformation, osmosis, hydraulic head, hydrocarbon buoyancy, and the following mechanism will be examined in the following session. Compaction, disequilibrium, hydrocarbon generation, formation uplift and unloading, smected geogenesis. Chillinger, etc. Shows more 10 causes of abnormal pore pressure in his book. Okay. Okay, let's begin. Examples of areas where compaction disequilibrium is cited as the primary reason of abnormal pressure includes Sakhalin, United States, Gulf Coast, Alaska Cook Inlet, Beaufort Sea, Mackenzie Delta, North Sea, etc. In these areas, the abnormally pressed rocks are mainly located in the Tertiary and late Mesozoic sedimentary formation. The depositional setting is dominantly delta, and the lithology is dominantly shale and sand. Formation uplift and erosion causes overpressures. The example in this slide. Assume that the formation is perfectly sealed at burial depths D0, retaining a normal pressure of pressure 0. If it's uplift to the depths D1, and pore pressure will keep the original value after uplift. If the formation keep the original pressure after uplift, it will have overpressure compared at the new depth D1 to the current pore pressure. One more reason for abnormal pressure, this is hydrocarbon generation. Hydrocarbon generation is the production of mobile liquids fluid, mainly petroleum and hydrocarbon gases. They are generating from initially solid stationary kerogen, resulting in an increase in a liquid volume on porosity when the liquid cannot be expelled. Research on the Wheatstone Bakken Shale has long highlighted the consistency of overpressure and hydrocarbon production based in Montana and North Dakota, United States. The abnormal pressure is attributed to two processes. At first, at an increase in the volume of hydrocarbons and residues compared to the unchanged organic material. At second, due to conversion of solid organic material supporting the overlying rock formation into hydrocarbon pore fluids, preventing the structural collapse of the rock frame. It's estimated that the liquid volume increased by about 25%, with even a greater volume increase as the maturation process progresses from oil to wet gas to dry gas. Most shale oil and gas reservoirs in the United States and all the world have abnormal pore pressure, and high overpressure is common. Please note that the table on this slide. For example, in Haynesville and Bossier shale gas plays in Louisiana and Texas, pore pressure gradients are very high, ranging from 0.75 to 0.94 psi per foot. And the benefit of higher pore pressure gradients is high well production. It's more good than wells without high pore pressure. The pore pressure elevation is caused, maybe caused by hydrocarbon buoyancy effect due to density contrast between the hydrocarbon and water. The pressure elevation due to the difference in densities gradually decreases from the maximum values at the top of the reservoir to zero at the water and hydrocarbon contact. The concept of tensoroid effect, as I considered before, state that the pore pressure in the vent and the adjacent shale are only equal at the one depth, i.e. the centroid depth approximately at the mid-height of the reservoir. Aquathermal process is one more reason for abnormal pressure, because heating causes expansion of pore fluid at defined depths in a confined and relatively uncrustable rock matrix. Expanding pore fluid would lead, in theory, to pressure increase. Another cause of abnormal pressure are chemical reactions, as high dehydration reactions include transfer of gypsum to anhydride. Osmosis effect, defined as a spontaneous movement of water through a semi-permeable membrane separating two solutions of different concentration of one solution and water until the concentration of each solution becomes equal. Shale diapers and salt diapers are intrusion that causes stresses in formation and unpermeability prevents the fluid drainage. Okay, let's go to the topic number 4 as a pore pressure prediction method and discuss compaction and unloading curves and types of abnormal pore pressure. If the formation uplift, it called also unloading process. The relation between effective stress and sonic velocity doesn't fit a loading curve. If you see all at upper picture A, B and C, this blue curve, it's a compaction curve. on the chart effective stress and velocity on Y. Then this curve, this unloading curve, we see the difference between this curve. The unloading occurs along the flatter effective stress path than the initial compaction curve in the velocity and density curve. Upper capture also indicate that the density change very little in unloading condition than compaction condition. Okay, this is change of density in compaction condition, and this is a little change in the unloading condition. Jung and Weisniak studied the relationship of pore pressure, vertical effective stress, and corresponding P-wave velocities and densities in Bussiere and Hinesville shale gas formation, United States. Unloading may exist in a lower figure compared to Bohr's loading curve. This is a similar picture as previous slide, and please note that if we see on this curve, unloading curve, that the pore pressure model must be modified to account for this new relationship between velocity and effective stress. Yes, because along the red line we have a large change in the effective stress, but only small change in velocity. Okay, this is velocity in unloading condition, and velocity changes, and velocity changes in compaction condition. Okay, let's consider this picture once again. So this picture in previous slides. Okay, the formation, uplift, and erosion cause overpressures. We know it. This if the sand uplifts on any depths, for example for D1, that saved overpressure that was on depths D0, save on new depths D1. Okay, this is example of unloading process, because we had sand on one depth and it uplifts to upper depths, new depths. This is unloading processes. Yes, this is unloading processes. Okay, this is example for Zobak monography. There are basically two, he describes basically two types of direct compaction experiment, hydrostatic and confined, and this slide is this classic example of compaction condition. Yeah, the data shown on the picture, this capture, were collected in a confined compaction test, because it thought they would be similar to vertical loading in situ. And note that the application of moderate effective stress result in marked porosity reduction. Shale compaction data, such as that shown in capture, can be described by exponential function. This is function shown on this slide. This is founded porosity, initial porosity, exponent, empirical constant, and effective stress. Effective stress is defined as full stress minus biot or pressure. Biot, this is pore elastic constant. We will discuss it in future lecture. Okay, So we discussed unloading and compaction processes that they follow from this. Exists two types of abnormal high pore pressures. The first type is compaction, and second type is unloading. The compaction type defined by basically disequilibrium compaction area. This is can be exist if we have fast basin subsidence, high thickness of the clay layers, low permeability, high compaction, very high speed compaction that characterized in young oil and gas basins. For example, this is Sakhalin, where we can see miocenic deposits. Okay, and unloading type exists if we have fluid generation. When we have no fluid migrations path, when we have uplift of rocks from one depth to another depth. Okay, this is a combined example for two types of abnormal pressures. This is basically first type and second type. Let's discuss pore pressure prediction basics for shales. When we talk about predictions of pore pressure, commonly we are speaking about only shales, because shales work with Terzaghi effective stress principle layer, but sands doesn't work. Okay, and conventional pore pressure analysis is associated with shales. The effective vertical stress by Terzaghi, as I said before, this is a difference between total stress and pore pressure. But this is equation in another form, where total stress equal effective stress plus pore pressure. Maybe a biot here. The basic steps in performing one conventional 1D pore pressure analysis. This is 4 steps. At first is calculation of total stress, estimation vertical effective stress for either log measurements, either seismic velocities. Then calculate pore pressure as a difference between total stress and effective stress, and calibration of existing information that it's available for us as a modular dynamic tool, MDT, RFT, any gas showing data, kicks, cavings in wells, etc. This is the simplest Eaton's effective stress method for estimation of pore pressure in shales, that based on Terzaghi effective stress calculation. Okay, this is pore pressure that we calculate. This is total vertical stress that in the simplest form can be described as integrating of density by depth. and effective stress. Yes. Effective stress can be right as as resistivity, porosity, density, acoustic, dx point, etc. This method will be considered by me in future slides. And at first, let's consider Eaton's method by acoustic logging. I remind that Eaton's method works for first type of abnormal pore pressure. To use Eaton's method, at first we can calculate normal compaction trend. The normal compaction trend line shown dotted blue line in this picture. Based on normal compaction trend line, the expected pore pressure is calculated, and the effective stress is calculated for all depths. This is dt slowness of P wave on normal compaction trend line, and dt observed. This is fact P wave slowness. The equation for normal compaction trend line for this curve described here. We know porosity, and mudline, and related between the normal porosity and mudline porosity, we get this equation. This equation defines normal compaction trend line for Eaton's method, where we use mudline data and constants. This is example for Eaton's method by slowness and calibrated on RFT, repeat formation tests. I'm sorry, I forget to write reference. I'm sorry. Moment. Okay, let's go. This is a complex example for using of Eaton's method by P wave slowness in Western Siberia. On this slide you can see the wells where we have P wave slowness for each well. After this we will calculate normal compaction trend line by this equation. The input P wave slowness is blue line, and normal compaction trend line dotted red line. Then after calculation by this formula, we get pore pressure distribution for all wells, and calibrated in MDT data for each well. As you can see here, the anomaly of pore pressure can reach 2 grams per cubic centimeter. This is very big abnormal pore pressure. It can cause problems while drilling, because it's for drilling of this wells, we need the heavier mud weight, then we need it in little pore pressure. Also we have gas showing kicks and another drilling events. Okay. Also, this is one more example for Eaton's method by P-wave velocity in Western Siberia. For input, as an input data, we use one moment, please. We use P-wave slowness after shale line selection calculation of normal compaction trend line. Okay, and using of Eaton's method for calculating of pore pressure profile. This is calibration of on NDT. This is total vertical stress. Total vertical stress gradient. Sorry. You know that the rate penetration increases in undercompacted on overpressed shale. So the increased ROP may be indicative to abnormal pore pressure. However, there are also many other factors as lithology, differential pressure, weight on the bead, rotating speed, bead type, and change of bead. Therefore, the only ROP is not enough to be used the detection method for abnormal pressure prediction. Scientists Jordan and Charlie supposed to use the exponent as one of real-time pore pressure prediction method. The formula for the exponent you can see on this slide. Okay, it depends on ROP. It depends on ROP, rate of penetration, rotary speed, weight on bead, and hole diameter. But the exponent is also dependent of differential pressure. That is the difference between mud weight and pore pressure. Okay. The exponent needs to be corrected to reflect the change of mud weight. This is showed by yellow light. Using the correct the exponent, the empirical equation for pore pressure can be written similar to resistivity of acoustic method. This is showed in green light in lower part of the slide. Figure at right part of the slide presents a post-well analysis in a shale gas well for applying the corrected the exponent method to compute pore pressure. After calibration, the normal compaction trend line by the exponent can be used for real-time pore pressure prediction. Also, the porosity can be used for prediction of pore pressure by Eaton's method. The principal scheme of working with method you can see on this slide. On first type we have distribution of porosity on for all cross section of well. After this, it's need to build normal compaction trend line. Okay, and difference between normal compaction trend line and observed porosity, this filling area, it's related to abnormal pore pressure. Okay. This is description of pore pressure prediction for porosity. We have and first step a relation between porosity and effective stress. Then this go to for a relation between normal compaction trend line, and on the final step we get distribution of pore pressure gradient in terms of porosity by Eaton. An important step in performing pore pressure analysis is to select clean shales in well-logged data, because pore prediction theory is based on the undercompaction mechanism of shale. I talked about it on previous slides. Therefore, gamma ray data in well-log can be used for a differential shale interval from those of other lithologies. Before applying the porosity model, one needs to obtain the shale porosity from density log or acoustic log. And drawing shale baseline, the first step is density and divide and separate shale from other rocks. It's shown in figure. All rocks that we see on left part, this is sands. Okay, sands, and on right border of shale line, clays. And next calculation is used only for clays. The shales doesn't account for. Okay. This figure presents another example of pore pressure analysis using porosity data. The porosity obtained from density log and calibrated to core data. The calculated pore pressure increased from Booster formation. In the Booster and Hinesville shale, the porosity is significantly higher than a normal porosity trend, and hard overpressure exists. And pore pressure obtained for the porosity method and sonic logging method have a similar result and match the kick data. Kick data is green dots. Okay. Based on a relationship of measured resistivity and burial depths in the formation with normal pressures, was proposed the following equation of Eaton's method by resistivity logging. Deeper than depths of 5 kilometers, the formation is slightly undercompacted with a lower resistivity than a normal compaction trend. Yes, upper this depth. From this depth, 7.5 thousand foot, the formation is further undercompacted and more elevated pore pressure exists. Compared the measurement pore pressure, the modified Eaton's resistivity method gives a obvious good result in pore pressure calculations. So good as previous methods. Velocity, acoustic velocity, density, porosity, the exponent, and another method. On this slide I want to show published method of pore pressure prediction, but I see it rarely than Eaton's and Bauer's method. And the next method I won't discuss, this is Bauer's method. This is method for used calculation and prediction pore pressure of second type. This is associated with unloading. Borrowers calculated the effective stress from measured pore pressure data of the shales and overburden stresses and analyzed the corresponding P-wave velocities from well logging data in the one of deposit of Gulf of Mexico. He proposed the sonic velocities and effective stress having a power relationship, and because of effective stress and P-wave velocity don't follow the loading curve if uplift on unloading process, and a higher velocity in the unloading curve that in loading curve process appears. At the same effective stress, Bowers proposed the empirical relation also to account for the effective effect of unloading. For abnormal pressure caused by loading and unloading mechanism, he proposed equations. I show them the slide, and we will discuss more it in future slides. This is one of the example of using Bowers method in published. You can see here a distribution of pore pressure and calibrated it of repeat formation testing data. Another method for calculation and prediction pore pressure of second time, it's Miller's method. This is very similar method as Bowers method, and it includes unloading and compaction part, and it can be used for calculation of pore pressure types that associated with generation, uplift, etc. Okay, let's see on derivation of pore pressure and make any conclusions that we discussed earlier. The indicators of changing of pore pressure in cross section, main indicators. This is porosity, sonic, P-wave velocities, resistivity, the exponent, density. Also, additional indicators then we can consider in our lecture can be total gas, because total gas should increase when we have underbalance drilling occurs in, for example, gas bearing formation. Background gas, connection gas, gas cut mat, ROP as a rate of penetration. ROP increase why we have anomaly high pore pressure. The exponent, pressure while drilling and temperature, mud volume, cuttings increased of in case of instability of abnormal pore pressure, hole fill, overpulls, tight holes, pug holes, etc. Another drilling events. The drilling events, trouble plots, we will consider in future lectures. I found the examples in YouTube with fluid showing examples. Let's try open the video.
Не прошло и недели с момента ликвидации последней аварии. 19 июня 1998 года оперативная группа Сургутского военизированного отряда выехала на Федоровское месторождение. Обстоятельства, при которых произошла авария. В процессе проведения работ по отсыпке на 453-м кусте при маневре в опасной близости от устья эксплуатационной скважины номер 5049 автомобилем «Татра» был допущен наезд на фонтанную арматуру с повреждением кабельного.
The important part of pore pressure prediction, this is real-time pore pressure calculation. The real-time, slow-time P-wave measurements used to pore pressure calibration in place. Yeah, we have calibration points. We can build a normal compaction trend line and estimate the pore pressure in the case and find down potential kicks prediction. Okay, now we will consider topic number 5, pore pressure measurements. The calculated pore pressure distribution profile must be calibrated, and one of the calibration method is pore pressure measurement. Wireline formation testers are used to obtain pore pressure, formation fluid samples, and permeability indicators. Among the most well-known wireline formation testers are MDT, modular dynamic test, Schlumberger, RFT, repeat formation tests, XPT, and another pore pressure measurements. As for shales, this case is most difficult for pore pressure measurements, because in shales there is most unpermeable formation, and in this case the most good method for pore pressure measurement is DEFIT. This is method in which happened hydraulic fracturing, and after hydraulic fracturing is pore pressure measure happens. This is example of pore pressure calibration on one of Russian oil and gas deposits. This is MDT. Another calibration pore pressure profile by MDT in Sakhalin oil and gas deposit. In this slide you can see the pore pressure prediction in real time. The green points as MDT by real time. And one of problem while pore pressure measurements is supercharging effect. This effect occurs because the permeability of mud cake on the wellbore well is not zero. The mud cake, even with low permeability, allows continuous penetration of drilling fluid filtrate. In low permeability formation, the resistance to filtrate flow created by the mud cake may be equivalent to the resistance of the formation to exit filtrate. Thus, the measurement takes by the formation tester will not reflect the actual pressure information, actual pore pressure, since there is a pressure difference between the pressure on the surface of the mud cake and the pressure in area of the formation not affected by drilling. The supercharging effect dots are red dots on this well section, and this not conditional information. And while audit and checking input data, the supercharging point not used in future work. Okay, now we will discuss pore pressure calculation in LithoStudio software. Okay, to continue the calculation of pore pressure, please open the pore pressure master from Geomechanics tab. And for this task, please select calculation method is Eaton methods. For overburden stress gradient, please leave the OBG curve as default. For hydrostatic pore pressure is 1 gram to centimeter cubic. As a normal compaction trend, we will use NKTL dt, and observed compaction trend. This is curve that we have already filtered. We will use this curve, and coefficients m and a for Eaton's equation. Let's leave as default. Curve name is PPG Eaton. Pore pressure gradient, output curve is gram per cubic centimeter, and depth unit is meter. Okay, run. Now move the PPG on curve, on track, and let's estimate calculated curve. Don't forget use your well testing data. This is from well testing folder, pore pressure gradient, and let's look what we have already get. Okay, one moment please. Don't forget use your lithology column and stratigraphy. Okay. I prefer to use another coefficients, for example 3. Not good. For example 1. Good. For example, instead of1.02, not good. 0.96, more better. Okay. Now we will draw approximated curve that will be use these points and will make hydrostatic pressure here, because the calculation by Eaton's method in these rocks is not correct, because this is magmatic rocks and the Eaton methods doesn't work for magmatic, only for clastic claystone rocks. To draw new curve, let's use draw curve and make a first point at 1. Okay, let's approximate the curve. Okay. Okay. Now, yes. And as a first point, let it be from 0 meters. Okay. Let make curve name PPG definition. Okay. Let's put the mud weight static on this curve. Now we will see that mud weight static intersects our curve in interval Bajan, but we don't see any blowouts here. This can be explained that BA layer, this is unconventional formation, and this is no permeable interval, and the absence of blowouts don't explain don't means that mud weight static cannot be bigger than a pore pressure gradient. Let's leave as here. Okay. At last, let's make the wall section by pore pressure calculation. The first track let be stratigraphy, then lithology, then gamma ray, shale point DT, shale line DT, shale point DT. Let's on this track, backward scale and logarithmic scale. Track number 4, let's delete. The track number 5 is calculation of pore pressure gradient and calibration on pore pressure points in permeable zones. And final track, let's delete. Okay, let's rename the project for pore pressure this well section is folders in visual sections, and all curve with calculation of pore pressure in stresses. Okay, don't forget to save. This is reference and most recommended books, literature about pore pressure, and this is used in our presentation today. And this presentation made with SlidesGo template. Thanks, SlidesGo.